first of all, thanks to the organizers for inviting me to give a talk here. Let's see it as a great honor. Okay, so I will talk about Reinhardt reflection. Well, it's about the relation between truth theory on the one hand, truth theory in the Kripkean sense of the word, and set theoretic reflection on the other hand, weak set theoretic reflection on the other hand. So my talk is going to be very impressionistic. There's not going to be any real proofs, and there's going to be some imprecision mathematically even. And then, so no proofs in the talk in the good Kripkean tradition that we heard about just now. And this is very much still work in progress. It's work in progress with Carlo, who's here, and with Philip Wells from Bristol and Martin Fischer from München. Right, so that's what the talk is about. So, and it's going to be about a paper by Reinhard. So in 1986, Reinhard published a paper, Some Remarks on Extending and Interpreting Theories with a Partial Predicate for Truth. And the truth theory that he had in mind was the Feferman theory, the Feferman system KF. So Feferman worked this out in, it must be 1978 or 79, and manuscripts circulated. And he gave talks about it. And Reinhardt was familiar with the KF system already then, even though Feferman's paper was, in the end, the final version was published only in 1991, and the final version was pretty different from the early versions. So Reinhardt's article in 1986 had kind of a slow start, I think. So for the first, certainly 15, but maybe close to 20 years, I think not many people read it, not many people commented on it. But since then, so let's say from about 2005 onwards, this has changed. And by now it's one of the most famous articles in formal truth theory, and rightly so, I think. So most of the work so far that's taken off. So the reason why this paper has been so influential is the first part of the paper, where Reinhardt makes the distinction between KF and the internal logic of KF that we already heard about, and he asked some questions about it. And this has sparked a line of research that has, I think, sort of culminated in recent work by Carlo and Volker Halbach, who kind of gave the final answer to the last Reinhardt question that was still not fully answered. Okay, but we're going to focus now. I'm going to focus, but I'm talking about, I'll speak in plural, not in the majestic sense, but just because it's collaborative work. Second part of the article. This has baffled commentators, this second part of the article. We will try to make some sense of this. So in part, this paper, my talk is going to be exegetical in nature. And I will argue that when taken literally, we can make perfect sense of it, but it doesn't quite work, what Reinhard is trying to do. But below the surface, we find deep insight that has potential, I will argue, and this potential is probably, or this is what I kind of suspect, not been exploited yet. So welcome to the Bible study group. It's going to be like reading the Old Testament, seeing some contradictions, and trying to nonetheless draw models from. And actually, we, Carlo and Martin and Philip and I, we had this little study group. So last year, every week, we met for an hour on Zoom, and we tried to make sense of this. Okay, so let's see how far we got. So this is the structure of the paper the talk that I'm going to give. It's not very exciting. I will go through the first parts very quickly because all of you have the relevant background. So we want a good theory of self-referential truth. That's what was Saul Kripke's aim. And he gave us one in 1975. It has been talked about a lot already. And it's a theory in the semantic sense of the word, if we use the terminology of the philosophers of science. So he gives us a bunch of models. He also is quite aware of the fact that that in some sense there's a problem with closure. So there's a famous quote: "The ghost of Tarski is still with us." We're Kripke clearly saw the limitations of what he had accomplished as well as all the positive stuff. So then this was axiomatized, finally published in 1991, and the result is the Kripke-Feferman theory. So I don't think I have to present the Kripke-Feferman theory anymore. We all know it, and it has been presented before today. So I'm going to start with where Reinhard comes in. So this is in 1986, and I'm not claiming I don't want to claim concerning this slide that Feferman, who was giving lectures about this kind of stuff already in 79, 83, was not aware of this. So certainly the first little theorem or lemma, well, that Feferman was clearly aware of. So if we've got this KF system here, and if we take a sentence which has no occurrences of the truth predicate, well, then the Tarski bicondition holds for it. Provably so in KF. So we have provable transparency for purely arithmetical sentences, as I will put it. Okay, good. So that's good. But at the same time, there's something which is not so good about this KF system. And that is it's in some sense internally incoherent, somewhat incoherent, even though it's perfectly consistent. So KF cannot prove its own significance, as Reinhard calls it. That means it cannot prove its own truth fully. So, for instance, if we take a liar sentence, then in KF we can prove the liar sentence, but also that the liar sentence is not true. So basically, KF says of itself, I'm not fully trustworthy. And it says that of itself. Not only is it not fully trustworthy, but it says so itself. It says that of itself. Okay, so Reinhard points this out, and he, at the same time, says this thesis that somehow this is problematic and it has to be solved. So he says, basically, a satisfactory axiomatical truth theory, self-reflexive or type-free truth theory, should prove for each of its theorems that it is also somehow true. That's what he says. Okay, now literally speaking, that cannot work. I mean, there's no straightforward way of doing this because KF cannot be consistently closed under the truth necessitation, as we all know. Okay, good. So, Reinhard tries to find a way out of this. And basically, what he is sort of suggesting, even though he doesn't fully embrace it, is that we move from the background setting of arithmetic to a background setting of set theory. And I think that's a crucial move that he should have fully embraced. So, okay, so I'm going to talk about the language of set theory. ZFC is the standard system for it. V is the set theoretic universe. V alpha is the ranked initial segment of V up to level alpha. So this is all standard terminology. And then we have within set theory this idea of set theoretic reflection, that V is semantically similar to certain small parts of V. This can be cashed out in various ways in precise mathematical terms. But basically, what we can say without real loss of generalization is that when we talk about small part, we can interpret this as rank initial segment, as a V alpha. And semantic similarity, we can cash out as some sort of elementary equivalence relation, holding between V and this initial segment V alpha. And this move then involves a relativization of the quantifiers, because if you evaluate a formula in this restricted structure, in this initial segments, you relativize all the quantifiers to this V alpha, because you want to focus on that structure. Okay, and then the most basic reflection principle, it goes back to the early 50s, is this Montague-Levy reflection scheme. And this is a basic version of this basic reflection scheme. And it says that if you've got a set theoretic formula, phi, then if phi, then there's also a rank initial segment, V alpha, such that when you relativize all the quantifiers of phi to this V alpha, the thing also holds. That's basically what it says. And there are variations of this Montague-Levy reflection scheme, and we're going to be concerned with at least one or two of them. Okay, Montague and also Levy probably proved that ZFC can prove Montague-Levy, this scheme. But at the same time, in those early papers, it's clear that this scheme does have some strength. So if we take away foundation and infinity from ZFC and put instead Montague-Levy in, then we get back ZFC. So foundation plus infinity are equivalent to Montague-Levy against this background of ZFC minus foundation and minus infinity. This is more or less true because you need a little bit strengthened version of this Montague-Levy thing, but that's the message. Okay, so Reinhardt's general idea seems to be the following, is that the internal incoherence problem for KF that we talked about can be solved, or at least alleviated, by making use of set theoretic reflection. As I said, he doesn't fully embrace this thought, as we will see, but that's the direction it's going, and I think it's fundamentally right. Now, commentators have struggled to make precise sense of his suggestive remarks on this matter. So here they are. So I'm just going to quote this whole long passage where Reinhardt makes his suggestion, and which has puzzled people. The especially important sentences are in blue, and they will play a role when I comment on these passages. I will refer back to these blue things. So here I start quoting Reinhardt. He says, I wish to suggest a simple general principle. The principle is a reflection principle because something is true in the absolute sense, with truth being a partial predicate. There are models with ordinary total predicates which reflect this. So it has to do something with reflection. I do not attempt to state this precisely and significantly here. Significantly means that I can also coherently state the truth of it. Here I only wish to state the following formal principle, which might be added to our formal theory. Writing A super T0 for the result of replacing the truth predicate, the absolute partial truth predicate, by T0 in A, the principle is that if A, then there is a total truth predicate T0, which is included in the absolute partial predicate, such that A super T0 holds. So that's my principle too, he says. Since all total principles have total truth predicates, this means that if A, then there is this T0, such that A super T0 is also true in the absolute partial sense. That's what he says. Okay, thus the theory allows for its own significant interpretation. So for each of its theorems, it can state, it can see that it's somehow true, at least piecewise, pointwise, right? Because it doesn't say that there's one T0 that does it for every A. For every A, there must be a T0. It's not uniform. Okay, and then there's an important footnote. So we talked about this famous footnote number 18, I think, in the outline of a theory of truth. Here's another footnote that in our Bible group became a bit famous. It's footnote 12. He said, oh no, not yet, not there yet. Next slide. So he continues. He says, I do not wish to suggest that these reflection principles can be adequately expressed in the language of KF, against the background of arithmetic, with no further explanation. The total predicates involved may not be expressible in the language of KF, so these T0 things. Nevertheless, I believe I've said enough to indicate how my proposal may be elaborated to clarify the status of non-significant sentences. And here the commentators say, no, you have not done that. We don't understand. But okay, so he says, oh, okay, if it's not clear to you, here's a little footnote. He says principles, so he wants to have at least some confidence in the consistency of principles like 2 and 2 stars, 2 prime. And he says this is how you get it. Principles closely related to 2 and 2 prime can readily be seen to be consistent, assuming large cardinals. For example, if kappa is accessible, therefore make set of C true, second order set of C even, but we don't need that. And we carry out a Kripke construction over the cumulative hierarchy V kappa up to kappa. We get a model, M is V kappa with the epsilon relation on it, and some sort of truth predicate, T kappa, which satisfies reflection in the following form. If sigma, then there is an alpha such that if you relativize the quantifiers in sigma to V alpha, and you cut off this truth predicate, T alpha, at this level, you cut off this truth predicate T kappa at the level V alpha, so T kappa is this Kripkean truth predicate, well, then that should hold. And then he says, well, evidently T kappa intersection V alpha plays the role of this T0 in 2. Okay, more precisely, there is this set T0, which is exactly T kappa intersection V alpha, which is total, and thus can play the role of T0 in 2. Okay, so I won't talk about this very last thing. But what are our first impressions of this? So far, that's Reinhard, and he doesn't really say any more than this about his suggestion, his sketchy suggestion. First, overcoming internal incoherence, or overcoming or alleviating, I would say, by appeal to reflection. And if we ask ourselves what kind of reflection and look at this footnote, then we might suspect it's maybe a Montague-Levy-like reflection. Because if we look at this thing again, yeah, this really looks like Montague-Levy reflection, right? It's just like Montague-Levy reflection, except that we have this extra predicate T in here, which is cut off. That's the alpha. Okay, good. And then it somehow exploits the provable transparency for KF. So the idea is that this should be a purely mathematical thing with no absolute partial predicate in there, just this thing in here, that's supposed to be total, so we can stick a T in front of it. Okay, good. But it's not easy to see precisely what he is trying to do, or at least it wasn't for us. And so one question is, what is the ambient setting precisely of the principles 2 and 2 prime? And maybe we should take this hint seriously that we move to a setting of set theory. And what are the principles exactly that he's after here? How strong are these principles? These are questions we want to ask. Okay, So we will take this step from the setting from the arithmetical setting to the set theoretic setting. So we take as our new background theory the language of set theory augmented with an absolute partial truth predicate. Okay, but we want to for this truth predicate we want to formulate these KF-like clauses, in particular that the quantifiers commute with the truth predicate. In arithmetic, that's no problem because we have canonical names for each natural number, but in set theory, we don't. There are various ways to solve this, but we take the Fujimoto way where we just say, okay, we move to a proper class size language where we have an individual constant for each set. And then we can unproblematically formulate the Feferman, the KF axioms for the truth predicate over this enormous language, over this big language. Okay, and then we can formulate Reinhardt's principles 2 and 2 prime in this language. So we're moving to a new object language, which is not quite what Reinhardt did. He just said, I want to give a consistency proof. I want to produce some models. But now we're going to move to a new object language. Okay, good. So now the following makes perfect sense in the object language. So again, it's a scheme for every phi now belonging to this proper class size language. Well, proper class size sounds perhaps a little bit scary, but there's nothing scary about it because it's just that we want a constant for each set. For the rest, there's nothing strange going on. If phi, then there is a level, a rank initial segment V alpha, such that phi holds with the quantifiers relativized to V alpha, and the truth predicate, this absolute partial truth predicate, intersected with V alpha. And I think this is Reinhardt's proposal. But there's a problem, and the problem is that we start from phi with a truth predicate, but that should be a strong, cleanly fixed point over V, right? That's the kind of models we're looking at on the left-hand side. But then on the right-hand side, we also want this predicate, no, it's called T intersection V alpha. We want this also to be a strong, cleanly fixed point, but now over this little structure. But by just cutting off at V alpha your big absolute truth predicate, you don't get a fixed point, not always, usually not. And there's a little proof here, but I'm not going to go into that. But we have a problem, because on the right-hand side, T intersection V alpha is usually not a strong, cleanly fixed point. This principle does not say what Reinhardt wants to say. So this is not exactly right. But we can easily fix it. Just say what we want to say. So let Fp of xy be the true theoretic formula that says that x is a strong, cleanly fixed point over the structure y. Y is a set structure. And basically Fp is the conjunction of the KF axioms. Because there is a little theorem that says that if you've got a structure with a domain and a subset of this domain, then it makes this this formula Fp holds of S and D if and only if S is a strong, cleanly fixed point over this domain. Right, and that's what we want to say. So that's what we have to add. That's what we have to say on the right-hand side. And then we can formulate what Reinhardt was basically after. So, and that's the following: RR sub SK. If we've got a sentence phi from our proper class size language, if phi, then there is a rank initial segment V alpha. and a strong Kleene fixed point over V alpha, such that phi holds with the quantifiers relativized to V alpha and the truth predicate interpreted as this strong Kleene fixed point over V alpha. That's what we want to say. So if you remember this earlier passage in Reinhardt, we've just replaced T0 being a subset of T by T0 is a strong Kleene fixed point over V alpha, basically. That's what we've done. That's all we've done. Okay, and then let's see what happens to this. So I think, of course, we cannot ask him anymore. Bill Reinhard is no longer with us, but I think he would have said, yes, that's what I should have said. I should not have cut off this truth predicate. So, but we can then prove in KF over ZFC, as we've defined it, that this basic Reinhardt reflection principle holds. And it's a straightforward variation on the usual proof of the Montague-Levy theorem, but we need an extra base case because we've got an extra primitive predicate, and that's a truth predicate. Okay, but if we look at the right-hand side here, this is just a set theoretic formula, no t's occurring. Right? This is just a little set. And we've got provable transparency for truth-free formulas. We had this in arithmetic for exactly the same reasons. We'll have it in the set theoretic setting as well. So we can stick a t in front of it. So that means that KF over ZFC can see for each of its theorems that that it is somehow true, in the sense that there is a mathematical correlate of phi, which is true, and that it can see. So, and that's what he wanted. It's got it, okay? But this truth predicate can in fact, this is all positive, truth positive. So this truth predicate can be moved to the left and then distributed over the existential quantifier. Axioms allow us to do that. And then we've got T of this whole thing on the right-hand side. And then the KF axioms also allow us to put this T in front of this whole formula. So that means that this whole thing is provably significant, to use Reinhardt's terminology, in KF. And this is more than what Reinhardt was even hoping for, because he says, well, you know, we cannot significantly say this in KF, probably, if you remember what he said on this long passage. But we can. So the statement in the corollary is itself provably significant in KF. So it's even better than he was hoping for. Well, the theorems on the previous slide can all be strengthened to the statement that there is a single such reflection point for very obvious reason. So the language L, so our proper class size language can take parameters arbitrarily high in the V hierarchy. So there will be no V alpha that will allow us to access all of them so clearly. But nonetheless, for large collections of sentences, we can have a reflection point that does it for all those sentences. Okay, that's not so important now. Now, I still have a quibble with this, or we still have a quibble with this version. I think this is what Reinhard was after, but it was not, it's not quite sufficient, because, let's see how much, okay, I'm doing sort of okay, I think. Because if we go back to this basic Reinhardt principle, this thing is supposed to express the mathematical content of that thing. And whatever expressing the mathematical content might mean in this context, and I admit that this is not fully clear, it would mean that they have the same truth conditions. this is true, then that is true. Yes, that's what this thing is asking for. If this holds, then that holds. That's what this provides. But what if that holds? Then also that should hold. If the mathematical content it holds, then this thing from what it is abstracted should also be true. They should have the same truth conditions. But that is more than this basic Reinhardt reflection principle asks for. Well, we just strengthen it a little bit. In the following way, we say that if we've got a sentence with an absolute partial truth predicate, Kripke truth predicate, there is an initial segment with a strong cleanly fixed point above it, such that the truths are equivalent. If one is true, then the other is true. If the other is true, then the first one is also true. Okay, and this looks more like the form of Montague-Levy that you need to get really this equivalence between ZFC minus infinity and minus foundation and but with Montague-Levy in there, or the whole ZFC. Okay, so this is not what he wanted to say, but this is what he should have wanted to say, I argue. I claim. Okay, and then also this slightly stronger reflection principle is still provable in KF over ZFC, analogously with the way we do it in this setting where we don't have this truth predicate, but only the epsilon symbol. Okay, and then again we get, because this does not have any occurrences of the truth predicate, by provable truth transparency, we can stick a T in front of it. Okay, good. But do we get this little bit more that we can prove the truth of this whole thing? No, because now we cannot get the truth predicate in front of this, right? So here, to this strengthened version, Reinhardt's suspicion does apply that this whole thing cannot be significantly stated in KF. Right. So the statement is not, the statement itself is not always provably significant. So if you take nasty phi's, like such as liar sentences, then this won't work. Okay, so now, good. So now I'm coming to the last part of the talk. It's going to be a short part. So the theory of self-reference, so here's a thesis by the two Kentaros, and these are a singing duo from Japan. They have this, they always sing about the same thing. It's always the same theme. The theme is that the theory of self-reflexive truth over set theory is non-trivially different from the theory of self-reflexive truth over arithmetic. And therefore, they usually want to work over richer settings than just first order arithmetic now. Of course, if you do second order or third order arithmetic, already these differences start to show up. And I think we get extra confirmation for the theme of their songs from what we have been doing. And the reason is that here in this richer setting, we get a flexibility, a proof theoretic flexibility that we just don't have in the arithmetical setting. In the arithmetical setting where we don't have reflection, right? You cannot reflect the headed omega to a finite number. It makes no sense, clearly. But now here we've got enough space so we can do it. So you can say, yeah, okay, so KF considers, for KF, all strong cleanly fixed points are equally nice, but Kripke thought that the minimal fixed point is especially nice. So what if we focus on the minimal initial fixed point? Of course, here the work of John Burgess that was already mentioned comes in. Can we do something like this for the minimal fixed point and not just all fixed points? Is a question you might ask. what if we're interested in intrinsic fixed points? So in the proof theoretic truth literature for Kripkean truth, there's almost nothing about intrinsic truth, and there's a good reason for it, and we already saw this reason in Michael Glansberg's talk. It's just that the class of intrinsic, if you look at more complicated notions of Kripkean truth, their complexity becomes so high that you don't have a hope of capturing this axiomatically in any meaningful sense. Already with the supervaluation, the air gets a bit thin, in my view, anyway. So intrinsic fixed point, and then the maximal intrinsic fixed point. What was it again? In a pi, something in a. Yeah. Okay, so that, yeah, that it gets more complicated. So no hope in axiomatizing maximal intrinsic fixed point truth in an arithmetical setting. That's why there's no literature about it. Supervaluation fixed points. Okay. Right. So for truth in all intrinsic fixed point or the maximal intrinsic fixed point, there seems to be little hope in the arithmetical setting. So. But now, well, here's kind of a little intermediate stage. Suppose we work in KF over ZFC, we already know what this is, but now we add NBG to it. So we add second order quantification to it, and just the NBG principles. But one thing, the crucial thing is, we do not add axioms postulating that truth commutes with the second order quantifiers. So that means that in some sense, we move to a setting where the language is not fully semantically close anymore. Then we can axiomatize truth in a minimal strong fixed point in a very simple way. So, of course, Burgess did something like this in a first order setting, but it's not very simple. In some sense, it's natural to do it his way, but it's not simple, I would say. So KF mu over ZFC in this second order setting is just KF over ZFC plus these NBG axioms. You have to some basic principles on how quantification over classes functions. Plus, you just say that T is interpreted as the minimal fixed point. Just say this outright. Okay. Good. Then we can formulate the corresponding Reinhardt reflection principle for this, for minimal, for the minimal fixed point. And now we cannot prove it anymore in KF over ZFC plus the NBG, plus the basic NBG axioms. And the reason is that now we've really narrowed down our class of models to initial segments where the truth predicate is interpreted as the minimal fixed point over that structure, not just any strong Kleene fixed point will do anymore. We could narrow down our class of models, so we won't be able to prove this in our background theory anymore. And then you can ask yourself, well, okay, does that mean it's unsafe or something? No, a little bit of reflection will give you this. So pi 1, 1 reflection added to KF mu over ZFC and the NBG things will allow you to prove it. And even this pi 1, 1 reflection is overkill. And I think here, if we want to investigate exactly how much reflection is needed, one has to go to admissible set theory. And what you basically want is something like reflection for admissible classes, one admissible classes, and maybe, yeah, something like that in that area. So not much. You don't need the weak compactness or something like that. It's way overkill. Okay, and but now let's go back to first order. And we might also say, okay, so what if we focus on one of these notions of other notions of Kripkean truth, for instance, minimal fixed point truth or intrinsic fixed point truth. I've just taken intrinsic fixed point truth here as an example, but what I will be saying holds also for these other notions, for instance, also for supervaluation truth. Well, then you could say, if you're interested in intrinsic fixed points, then you say that if you've got a phi, then there is a V alpha and an intrinsic fixed point above it, such that they're equivalent with each other, have the same truth conditions. So that this really is the mathematical content of that. Whether this is enough for being the mathematical content, I don't know, but it's certainly a minimal condition. And being an intrinsic fixed point over a little set structure, that's just in set theory very simple to define. Right? This is not a complicated thing. So now, if we know okay, so yeah, it's set theoretically very simple to define. But again, we will see that KF over ZFC won't be able to prove this thing because this narrows down our class of models. For instance, if you know of something that it is true in all intrinsic fixed points over initial segments, well, then you know that it has to hold absolutely. So that means that not all strong Kleene fixed points are okay. But for KF, they're all okay. So we've narrowed down our collection of models. So we need a little bit more to prove this. And then, well, again, some kind of low-level Bernoulli-Gödel should do it. But exactly what's the minimum that you need? Maybe it's a pretty trivial question. I haven't thought about it. Maybe it's not so trivial. I don't know. Okay, but this shows, I think, that here really this theme of the two Cantaros comes to the fore, because it seems that now in this set theoretic setting, we might get some sort of handle on axiomatizing intrinsic truth, because we could take a reflection principle such as this, just as a truth axiom. And then one should be able to prove that, for instance, this Kripke example, what is it again? This sentence is true or its negation is true, right? That's intrinsically true. One should be able to prove that it is true from this principle. Because this is just, we just compute this set theoretically. We know how to compute this set theoretically over a little V alpha. That's just a little, a very simple set theoretic argument. And then we push it up. So that means that also our absolute partial notion of truth is forced to be somewhat intrinsic in nature. Intrinsic fixed point in nature. Okay, so that's, and one could do the same for supervaluation and so on. For instance, it might be interesting to compare what taking something like this as an axiom, how that compares, how taking this as as an axiom, but here the supervaluation fixed point instead of intrinsic fixed point, compares to something like the system VF over ZFC. I think that might be somewhat interesting. So I think I'm going to, yeah, of course, there are proof theoretic strength questions, but also a question that it's a very vague question, that's what I want to close with, is if you look at principles such as this, then what in Reinhardt-like terms, he would say, well, this somehow expresses the mathematical content of something that may possibly be very paradoxical, ungrounded, and what have you. But how interesting is this mathematical content? So I don't really have a good answer to this. And of course, you can strengthen these principles by asking more than this just being a V alpha. It could be a V alpha of a special kind, in the same sense as the sense in which James and Parkomov we're looking at reflection principles, proof-theoretic reflection principles, proof-theoretic-like reflection principles, where they say, well, we do not want to require there just to be a model. We want there to be an omega model of this thing, and then you say something stronger, or a beta 1 model or something like that. Some similar moves should be possible to carry out similar moves here, and that kind of brings, I think, yeah, so there might be something interesting about these rather low-level reflection principles, nonetheless, both from a proof-theoretic point of view, and maybe even both from a truth-theoretic point of view, and maybe also from a proof-theoretic point of view. Okay, thank you.